Look at the metrics of this physical event. A volume of less than 1 cubic micrometer, a lifespan of roughly 100 picoseconds, and a core temperature exceeding 20,000 Kelvin. Conditions with these parameters typically belong to the interiors of stars or the impact zones of particle colliders. But this specific event is occurring inside a simple laboratory flask filled with water. This is sonoluminescence. It is the hydrodynamic transformation of diffuse acoustic energy into high-energy photons. The only power source driving this reaction is a standard acoustic field. The sound waves passing through this liquid carry an extremely low energy density of roughly 10 to the negative 4 joules per cubic centimeter. Generating plasma-level heat typically requires chemical combustion or a high-voltage electrical discharge. Here, the entire process relies entirely on mechanical sound waves. The immense disparity between that faint acoustic input and the brilliant optical output represents an energy concentration increase of 12 orders of magnitude at a single focal point. To understand how this physical paradox operates, we have to trace the transfer of energy step by step, from the initial acoustic trapping of a gas bubble to the creation of a microscopic plasma state. This provides a clear example of classical fluid dynamics forcing matter to its absolute physical limits. The system requires a highly specific set of initial boundary conditions to function. We start by tuning a standing acoustic wave to a frequency between 20 and 50 kilohertz. This wave is driven into a liquid medium at an intensity of 1 to 10 watts. This dashboard illustrates the acoustic trap. A standing wave creates pressure antinodes, holding microscopic gas bubbles perfectly still. During the rarefaction cycle, negative pressure drops sharply, overcoming the liquid's tensile strength. The trapped bubble expands quasi-statically, swelling to a maximum radius of 100 micrometers. In fluid dynamics, this is a slow process. The expansion phase takes 10 to 20 microseconds to complete. Throughout this slow stretch, the gas inside the bubble functions isothermally. It maintains thermal equilibrium with the surrounding room temperature liquid. By pulling the liquid outward against its own resting pressure, the acoustic wave has wound a hydrodynamic spring. The system is now storing immense potential energy, primed for a sudden and violent release. The trigger for inertial cavitation is the sound wave's oscillation. The rarefaction cycle ends, rapidly transitioning into the high-pressure compression phase. External acoustic and hydrostatic pressure combine, abruptly halting the bubble's growth to force a reversal. The physics governing this collapse are wildly asymmetrical compared to the slow, steady expansion. The liquid rushes in with tremendous inertia. The bubble wall accelerates inward, breaking the sound barrier to reach velocities exceeding 100 kilometers per second. This nanosecond implosion creates strict adiabatic compression. There is no time for generated heat to diffuse into the surrounding liquid. Following the ideal gas relation for adiabatic processes, as volume decreases drastically without heat loss, the internal temperature must exponentially increase. The mechanical volume reduction factor is between 100,000 and 1 million. That precise compression ratio forces the temperature of the trapped gas to spike by 4 to 5 orders of magnitude. As the walls close in at supersonic speeds, they generate overlapping internal shock waves within the shrinking volume of gas. In the final picoseconds of the collapse, these internal shock waves produce ionization fronts, concentrating the kinetic energy even further into the absolute center of the bubble. The liquid's mechanical inertia operates as an unstoppable spherical piston. It brutally forces the room temperature gas into a state of extreme high-energy density plasma. Above 10,000 Kelvin, the trapped gas's molecular bonds strip apart, leading to complete ionization. This is why experiments often use dissolved noble gases like argon or xenon. Because they lack internal vibrational modes to absorb energy, the localized adiabatic heating effect is maximized. The result is a high-density, non-equilibrium plasma state, confined to a radius under 1 micrometer. The challenge for physicists begins here. The light-emitting volume is smaller than the 250 nanometer diffraction limit of visible light. Compounding the spatial problem is a severe temporal limit. The extreme flash event lasts for only 10 to 100 picoseconds before high internal pressure forces a rebound. These dual limits create a diagnostic blind spot. It is physically impossible for conventional optical microscopes or street cameras to pinpoint exactly what mechanism generates the light. The leading thermal model is thermal Bremsstrahlung. It suggests the light is emitted as radiation when free electrons collide with ions in the superheated plasma. The competing recombination radiation model posits the photon flash is generated precisely when ions recapture their electrons as the plasma begins to cool. Exotic hypotheses like the Dynamical Casimir Effect argue the extreme acceleration of the bubble wall might actually tear photons directly from the quantum vacuum. While we have mapped the classical fluid dynamics of the collapse, the final conversion of mechanical energy into photons remains a profound theoretical impasse. We can contextualize the severity of this event by comparing the interior temperature of the collapsing bubble, over 20,000 Kelvin, against an astrophysical baseline. This chart shows the comparison directly. The 20,000 Kelvin temperature generated inside the bubble is significantly hotter than the 5,778 Kelvin effective surface temperature of our Sun, yet their origins are entirely distinct. Astrophysical plasmas are sustained by immense gravity and continuous nuclear fusion over millennia. Sonoluminescence achieves these stellar conditions mechanically. It relies purely on the inertia of collapsing fluid to reach plasma states in fractions of a microsecond. Decoding this microscale energy-focusing mechanism provides a highly accessible tabletop proxy. It allows researchers to study extreme states of matter without the need for massive particle accelerators. This has direct implications for inertial confinement fusion research. To initiate a fusion reaction, facilities must rely on staggering physical infrastructure to focus immense amounts of energy into a single point. By analyzing how a symmetric acoustic field collapses a bubble so perfectly, physicists can better model how to focus massive laser arrays into tiny, symmetrical fusion targets. There are secondary applications in advanced materials science as well, utilizing these transient extreme pressures to fabricate novel nanomaterials that require high-energy synthesis. By focusing acoustic energy 12 orders of magnitude, this simple combination of sound and water creates a transient star-like environment within a microscopic laboratory crucible.